Good morning.
Good morning.
Morning.
We're on chapter 15 examples, but I just wanted to make an announcement of we lost one of our classmates. There's a memorial service through UNF on a celebration of his life at 6 p.m. tonight. I'll send out the details. I know they sent it out to different students, and I didn't go through to see exactly if they sent it out to everybody within the Thermo 2 class. So I'll make sure to forward that out. So it's more of a celebration within UNF, a service they're kind of doing there. And I'll send out the details to the Thermo 2 class. So this one that I do at 9 and then the one that I do at 3, all those students, to let them know if they wanted to join in and be a part. Okay. All right. So switching from that somber news, we're on the examples from chapter 15. We did the lecture last class on chapter 15, and so now we're going to apply some of that. Okay, so the first one, let's see, let's do 15 dash 23E. Okay. Set up here. All right, so given, let's see what we got. Ethylene, which is C2H4, is burned with 175% theoretical air during a combustion process, assuming complete combustion and a total pressure of 14.5 psia. Determine A, the air to fuel ratio, and B, the dew point temperature of the products. Okay. All right, so we have ethylene. Which is C2H4. We have 175% theoretical air. We have a total pressure of 14.5 psia. And they want us to find the air to fuel ratio and the dew point. Let me write out what that is. Let's put out these. Air to fuel ratio and dew point temperature. Okay.
Real quick, what's the subscript on the P in the givens?
Total T.
Okay, gotcha. Thank you.
All right, schematic. So we have our combustion chamber. We have our fuel going in, which is C2H4. And then we have our air going in on the other side, which is 175%, right? Theoretical air. Okay. And then what comes out is our products. Okay. All right, so where do we begin this problem? Any ideas?
We want to get like our values for ethylene
Or values? What values?
or like molar mass, things of the nature.
We don't even have to go that far in this problem. Oh, molar mass. Yeah. So, sorry. Yeah, we can get molar mass. I mean, yeah, we do need that. Let me see. Or we could calculate it, which for the molar mass, looking it up, we have for C2H4 is going to be 2 times 12 plus 4 times 1, right? So we get 28, right? So we'll need that eventually, okay? Or it should be in a table in the back. Maybe. It's 826, but I want to make sure it's 827. Does it have our C2H4? No, it didn't have our ethylene in it, but we can get other ones in table. A-27E.
You can get the mass of the air.
The molar mass of air, yeah, we can do that. So that's in our 8.1, right?
Wait, for that molar mass calculation, did you pull those from the periodic table, the 12 and the 1?
And the air one. Yeah, and it's like 12.0 something, but I'm just, that, again, that doesn't really add to much accuracy to what we're doing.
Yeah, okay. Would it be handy to have a periodic table with us?
Not really. I mean, because really what we deal with is, the only one that you would have to ever calculate is the hydrocarbons, which is carbon and hydrogen. Like the others, you don't have to actually calculate. They're going to be in the table. So it's not really necessary. You're not going to get anything really extravagant that you got to pull that kind of stuff from somewhere.
Okay, thank you.
So in the book it has 28.97, but we could also, again, we could approximate this as like 29. Okay. All right. So we got those. Now what?
And we just divide it by the U.
Divide it. I mean, we don't know. So so this first part is air to fuel ratio. It's going to be units of it's mass of air over mass of fuel, right? So these units, if you really think about it, this is kilograms of fuel kilomoles of fuel. This is kilograms of air, kilomoles of air. So if we divide it, it doesn't actually cancel out, okay, the kilomoles, because this is not the same kilomoles, okay? So you would still have kilograms, you'd still have all the units there. So we got to get rid of the kilomoles, right? We got to know then the kilomoles of fuel and the kilomoles of air to set up this equation, right? So if we have put this in okay. So that allows us to use the molar masses, but now we need to figure out number of moles of air, number of moles of fuel. Okay. Where do we go to do that? Or what do we do? All right, so this is where we do our chemical balance. All right, so let's set it up, okay? I'm going to start with the actual. You'll know what I mean in a second the actual chemical balance. We have C2, H4, and then we have to figure out, I'll actually leave that blank for now. We have something here to put in, okay? And then we have O2 plus our 3.76 N2, right? So there's the 1 here plus 3.76, so there's 4.76 kilomoles of air right now. All right, and then that goes into our products, okay? And we have extra air here. So we are going to assume combustion is complete. So I didn't put an assumption thing here, so but assumptions. Complete combustion, okay? All right. That means all the fuel is going to burn, right? And then if it's complete, we don't know anything other than, as we talked in the lecture, carbon going to CO2. So products now are only CO2, so carbon going to CO2, because they didn't give us any information about carbon monoxide, CO. And then hydrogen going to water, right? Because they didn't give us any additional information about it doing anything else. Okay? And then we have nitrogen here, right? Because that's kind of along for the ride. It's in the reactants, it's in the products. And then if we have excess air, we'll have some extra oxygen that ends up in our products. Okay. All right. So then that means we get to put down some unknown, B, call it CO2. And I have H2O plus N2 plus FO2. Okay, so we have these unknowns here. The other thing we don't know is the air, okay? And there is a little something we can do here because it does give us a little information. Does anyone remember what 175% theoretical air means from the lecture?
Means we have exactly the amount of air that we need to combust plus 75% excess air.
Correct. Okay, so as a reminder, yeah, 100% is that perfect amount, that's stoichiometric. write it and make it legible. Okay, stoichiometric. And we're at 175%. So we have that 75%, as was said, more. Okay. So what does this mean in our balance? So we have then, if we were to know the stoichiometric amount, it would be 100%, right? Or a factor of 1 times this here. So the stoichiometric amount we're going to call A theoretical. Okay, so that's the stoichiometric amount. Okay. Now we don't have that. We have more than that, right? Well, our factor is actually 1.75 then times that. Okay, so we have 1.75 times that stoichiometric amount. So it's talking about this right here. I have that arrow. Okay, does everyone get that? So if we were stoichiometric combustion, it would just have a factor of 1 in front of it. Okay, and our actual combustion here, right, would be stoichiometric, but we have excess. Okay. Okay. All right. So then, when we look at this equation, how many unknowns do we got? We got A theoretical, we got B, we got D, we got E, and we got F. Okay, so we got 5, right? What equations can we use to solve for these unknowns, or some of these unknowns? So they start there. Any idea? Where do we go from here in a chemical balance equation? Way back in chemistry time, what did you do now?
Balance the molar masses.
Yeah, we balance. Okay, so we see when we look at our balance equation, we have carbons. Okay, to balance, we have hydrogens, right? Because there's hydrogens, we have oxygens, and there's nitrogens. So we have our balance equations. Okay, you know, if there wasn't carbon in our reaction, it was just hydrogen combusting, we wouldn't have a carbon balance, right? Or if it was just carbon, there wasn't any hydrogen, then we just have a carbon balance and then oxygen, nitrogen. Or if we were just combusting with oxygen and not air, right, then we wouldn't have a nitrogen balance. So you just look basically at the equation and you see what do we have, right? And that gives us 4 balances. Basically, we're doing 4 mass balances by separating out. Okay, so we have 4 equations. Okay, so we can set those up, but we have 5 unknowns. We still need another equation. But we can set this up for now. If we do this, carbon, we have 2 on our reactant sides, right? On the product side, we only have CO2, so there's 1 with times B, so that means we already have what B is, right?
How do we know there's not a coefficient in front of the ethylene?
How do we know? We're assuming it. Okay, so because this coefficient is just kind of like a scalar, right? So we usually take 1 fuel, like if we had 2, then everything else just goes up by 2. Okay, so we just assume 1 there. Okay.
Okay, thank you.
Let's say we had there are problems in the book, I don't know whether I'll get to them or anything, where they give you all of the products, like measuring it with a gas analyzer. So then you know everything in the products. Then both of your unknowns are what's in front of the fuel and what's in front of the air. But here we're assuming, you know, kind of what's going on in the products to solve, or what's going on in the reactants to solve for the products. So be in the reaction side. Okay. All right, hydrogen, we got 4 on the left. Wrong color. Just throw everybody off using green there. Right? All right, 4. And then we got 2 times D on the right. So we know D is 2. Right? And then we got oxygen. All right, so on the left, we got 2 times 1.75 times A theoretical equals 2B plus D plus 2F, right? If we didn't have excess oxygen, we wouldn't have to have this part here. But because we put in excess air, right? Because we have this more air than we need, we're going to end up with oxygen in the products. Okay, so that's why we have an F in this balance. Okay, N2, N, I just have. We have 2, make that a little neater. 2, 3.76. Then that's times 1.75 A theoretical equals 2 times E. Okay. Okay, the easy part here is 2 cancels. Okay, so we have that. But you know, when we look at the oxygen balance, we have B and D, but we don't have F and A theoretical. And then down here, we need A theoretical and E. Okay, so that's, we have, again, because we have one more unknown than we have equations. All right. So we need to figure out another equation to solve for this. So any ideas on how to get this A theoretical? So what does it mean? What is that A theoretical? What did I say it is?
It's from stoichiometric ratio, right? So 14.7 something?
Well, that's for gasoline is around 14.7, but we have our values C2H4. Okay, so we need to figure out what that is, what the stoichiometric value is. Okay, so what we do is we just do a quick balance for stoichiometric. Okay, so that means we just set it up C, and we just have A theoretical. And I use the same coefficients in front of my thing because it's just habit, but they're not the same BD, because this is for excess air combustion in top. Down here is for stoichiometric. So they're going to be different values of B, D, and E. Okay. And this time we still have carbon, hydrogen, oxygen, nitrogen. We have 2 carbon, and then that equals B on the products, hydrogen 4, and we have 2 D. So again, we get, they don't necessarily have to be the same. Okay. And then oxygen, we see we just have A theoretical. So we 2 A theoretical B, or sorry, 2B plus D, right? We don't have the F there anymore, right? Because it's the perfect amount, stoichiometric, so there's no excess oxygen. All that oxygen's going into CO2 and water, okay? It's all going here. Now that's right here. Now we have B, we have D, so we would have a theoretical. In this case, that is something. 3. Right? And we don't actually need to do the nitrogen balance. Okay. Any questions so far? So the atheoretical we have now, right? So this is kind of here for now. We can bring it up and use that. Let's do it here. Right here, right? And right there. Okay. So that now allows us to say we have this, and now the only unknowns in this equation is F, and then this one is E. Okay. So we get, when we solve, we get F equal to 2.25, and we get E equal to 19.74. Okay. Any questions? All right, so let's go back. Now we're back up here to our air to fuel ratio, right? So let me rewrite it. All right, so we need our moles of air, right? What is our moles of air?
Would that be the 1.75 times A theoretical?
Mostly there. There's one thing we're missing. Okay, so 1.75 times our A theoretical. Let's write that in there. Okay. And then there's this that we're multiplying times, which is our 4.76. Okay, because this is just our multiplier, and then everything in brackets is air. Okay, so this is air. We're having this times that amount of air, and there's 1 plus 3.76. So there's 4.76 moles of air inside these parentheses. Okay. And all that would get us our kilomoles of air. And then we had 29 kilograms of air per kilomoles of air. Okay. Fuel, you know, we said 1, right? We assumed 1. And then our molar weight, we got 28. So if now we check our units, kilomoles of fuel, cancel, kilomoles of air, cancel. So we have kilograms of air per kilomole of fuel, which is the air to fuel ratio, okay, because it's mass of air over mass of fuel. All right, we just have to put in our A theoretical in this case. right? So these are the main parts that change right here, depending upon, you know, for this fuel, if we were given a different excess air, or if it was just stoichiometric combustion, then you would just have this factor in front would just be 1, not 1.75. That's what changes, okay? Other than, you know, they can change the type of fuel they give you, but that's really what changes. If you keep the type of fuel consistent, you can just then change the amount of air, and that's really what changes in this balance, is that factor, and that a theoretical is the same for a given fuel. All right, so if we crunch the numbers, beep, boop, 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 and we get 25.9. I keep doing this in these English problems, so I have an English problem, and all this stuff that I wrote should be in English units for the ratio. So this should be pound mass of fuel, pound mole of fuel. This should be pound mass of air, pound mole of fuel. Okay. And then down here, the same thing, canceled kilograms.
I'm sorry, where did we get the 4.76?
Yeah. The 4.76 comes from what's in the parentheses. Okay, so this is just our multiplier here, this 1.7 times a theoretical. But inside the parentheses, we already have 4.76 kilomoles of air, because we have 1 of oxygen and 3.76 of nitrogen. So there's 4.76 kilomoles of air inside the parentheses. And this, we're multiplying times that 4.76, okay? So that's where that 4.76 comes, and that's the most common mistake I'll see in the air to fuel ratio calculation. All right, so we get our 25.9 pound mass of air per pound mass of fuel. Okay. Any questions? All right, so that was part A. Part B is our dew point temperature. Okay. So with that one, we bring in our other chapters, and I kind of talked about how we would do that in the lecture, but I'll write down what the dew point temperature is, and we'll go from there. Dew point from chapter 14 is the saturation temperature at the partial pressure of the water vapor. Okay. All right, so knowing that, that means we need to get this partial pressure of the water vapor to get Tsat, right? We gotta get this first, and then we can go and get that. Okay, so how do we get the partial pressure of the water vapor? we have, let's first start off, what do we got given to us? We have the total pressure, okay? So that is the total pressure of the exhaust, okay? It's 14.5 psia. So if we know that, is there any kind of ways to then get what we would have for then the water that contributes to that total pressure of the exhaust, right? So we have then, right, so they gave us the total pressure, which is what all these, the exhaust, the products give us. You know, if we put all those together, we have a total pressure of 14.5. This is where we bring in some knowledge from chapter 13, okay? And when you sum up a mixture, you sum up the pressures of a mixture, they equal the total pressure of the mixture, okay? So if we have our pressure of the water, okay, and then the total pressure, okay, of the products pressure, okay, it's going to be the same as the number of moles of the water vapor over the total moles of the products. So we have product pressure, right? 14.5 psia, right? We're looking for this, what the water vapor's pressure is. Okay, so that means we better have a knowledge of the vapor's moles and the product's moles, and that's just D is the vapor, and then the products, you just summing B, D, E, and F. Okay. You basically get 2 pound moles over 25.99, or all right, so if we do that, now we have the moles of water vapor 2, and then the products, we just summed up everything that I circled in orange, okay? So then our only unknown, we take this ratio of 2 divided by 26 and multiply it times 4.5 psia, and that's our pressure of the water vapor. So the water vapor contributes 1.16 psia to that 14.5. Okay, so now we have that. We have our partial pressure of the water vapor. So now what do we do?
We need to find the saturation temperature of water at that pressure.
Yeah, so then we just go, we just go to the table. It's A-5E, and at that pressure, we just look at what's the saturation temperature. And we get 105.4 degrees Fahrenheit. Okay, so as soon as that exhaust hits that temperature, the water is going to start condensing out of that exhaust products. So as soon as those products, whether it's this, exhaust pipe, is that cool, or the air that it hits, is that cool, that it's dumping too, it's going to start condensing out and you're going to see dew. Okay. In my research, this is very important to know, because if I'm sampling the exhaust to try to get what's a part of the exhaust and measure these different components, I have to actually keep the temperature above that. Okay. I have to, anything in my sample lines, in my exhaust analyzer where it's measuring it, I have to keep it all above this temperature, and usually much higher above it, because you want to be careful. So then the water doesn't drop out, because if the water drops out, you're going to get a different measurement over here. So if this is gone, you're going to get different measurements for, because it don't measure the moles, it measures the mole fractions when you have an analyzer. So if you're removing water, you're going to remove and change your mole fraction that you're measuring. So in exhaust analyzing systems of exhaust products, you got to measure it with the temperature above that. The other way they do that is, the other method that they actually do is dropping out all the water on purpose before measuring, because then the water's not there, so you can calculate and correct for that. But you have to drop everything off of the water. All right. Any questions on the analysis? All right, let's do -15 -56. All right, 15-56, liquid propane, liquid propane C3H8 enters the combustion chamber at 25 degrees Celsius at a rate of 1.2 kilograms per, it says, just a second, kilograms per minute. I have a typo in the problem, okay, where it is mixed and burned with 150% excess air that enters the combustion chamber at 12 degrees Celsius. If the combustion is complete and the exit temperature of the combustion gases is 1200 Kelvin, determine A, the mass flow rate of air, B, the mass rate of heat transfer from the combustion chamber. Okay. All right. So we're given liquid propane, which is C3H8. We have the air, temperature of the air is 12 degrees Celsius, which is 285 Kelvin. We have the temperature of the fuel. It's 25 degrees Celsius, which is 298. Let's make that a little nicer. 298 Kelvin. They give us the mass flow rate of fuel, 1.2 kilograms per minute. We have 150% excess air. And then combustion's complete. In the exit temperature of the combustion gases is 1200 Kelvin. So the temperature of the products is 1200 Kelvin. Okay. Determine, we have to find the mass flow rate of air, and B, the rate of heat transfer from the combustion chamber. Okay. So basically our Q dot. So we have our fuel, C3H8, and it's at 25 degrees Celsius. We have our air, and it's at 12 degrees Celsius, and that's what's entering. We have our combustion chamber. I can keep my writing legible. And then our products exiting. And if I can keep my writing legible. And that's exiting at 1200 Kelvin, okay? Of heat. Okay. All right, analysis-wise. So starting off, let's figure out our mass flow rate of air. Okay. So what do we think we can use, or how we can solve for the mass flow rate of air?
Well, we were given mass flow rate of fuel going in.
Mm-hmm.
So that's one part of our mass balance. Then maybe we could explore a chemical balance to find, well, no, that would include both air and fuel. Well, that's a dead end.
What did we solve for last problem?
The air to fuel ratio,
Okay, and it's a ratio in what units?
pound moles of air per pound moles of fuel.
Right. So that's mass per mass, right? Right. So if we think of air to fuel ratio, it's the mass of air or the mass of fuel. Right. If we're keeping them in, we can also, at the rates, we could make this mass flow rate of air over mass flow rate of fuel.
Okay. So then we can just have a ratio of the two.
Yeah, so if we're looking for, let's say air in this one, so we, mass fluid of air to fuel ratio times mass fluid of fuel, right? We have this, we don't have this. Right? So what do we do to get that? What do we do to get the air to fuel ratio then?
The chemical balance.
Yeah. And I'm not going to spend as much time because it's the same procedure, okay? I'm kind of put the procedure down and then let you guys go from there. So we'll need a stoichiometric balance. The C3H8. And we can do our carbon, hydrogen, oxygen, nitrogen. I'll leave it up to you guys to go through all that again, but we'll end up with, from this one, the A theoretical being 5. And since our combustion is not stoichiometric, we have 150% excess air. So then we have our actual. So we said 150, so 1.5. Oh, wait, nope. I should take this back. It says 150% excess air. That is,
Wouldn't that add on to?
yes, so that's what I was getting at. Yep. Yeah, so that means it's beyond the 100% of the theoretical air. Okay, I was reading it too fast. I'm trying to go too fast. So it's now, the factor is 2.5. Okay, because there's the 100% theoretical air plus, in this case, because the last problem read theoretical air. It said 175% theoretical air. So this would be the same as saying 75% excess air, okay, in this last problem. Okay. In this one, they're telling us excess air, right? So they say 150% excess air. So that means that's 250% theoretical air. Okay, so that gives our factor there, right? That 2.5. Yep. So we end up with B3, D4, E something. 1.5 times 5. And F is our 2.5. All right, so let me write it. That's, E is 7.5. And F ends up being just 47. Okay. And then we can go through air to fuel ratio again. Air, we have, in this case, we have 2.5 times 5 times our 4.76. So in this one we are, okay, metric units, or SI units. Fuel, we again have 1 kilomole, and then our molar mass of the fuel, we can look, I think this one's in the back, or we can calculate 12 times 3 plus 8. Okay, but I'll check back. So for C3H8 in the back, we do have the molar mass that ends up being 44. Table A-27. Okay. So we get 39.22 kilograms air per kilogram fuel. So that means for our mass rate of air, we have 39.22 kilograms of air per kilogram fuel. And then our fuel was 1.2 kilograms of fuel per minute, right? So the kilograms of fuel cancels, and we're just left with kilograms per minute for kilograms air per minute. So we get 47.1 kilograms of air per minute. Okay, to have 150% excess air and flowing in 1.2 kilograms of fuel per minute, we have to flow in that amount of mass of air per minute. Any questions? So only just kind of using the air to fuel ratio was this part new. Everything else was very similar to last problem, right? Most of these problems all start out with something to do with the chemical balance to begin with.
Hey, Professor.
Yeah.
Where'd the 29 in the numerator just above
This one?
44? Yeah, 29 kilograms of air per kilogram fuel.
It's the molar mass of air.
Okay. Is it, so it's kilograms of air per kilogram fuel?
Oh,
There's-
okay, yeah, thank you. I was just going, yeah, I'm going too fast. So that's kilograms of air per kilomoles of air.
Okay.
Yes, cancel, thank you. So then we're left with the kilograms air per kilogram fuel. Other questions? No. Okay. All right, so then part B is more of the new part to this question, is our heat, okay? Our heat transfer. Okay, so where do we start with that? If this was not chapter 15, where would you start?
Yeah, I agree with Josias. He's put
Oh,
in the
yeah.
chat. Kiwi.
Yeah, COE, right? So heat transfer, we're looking for COE. So now we just need to utilize the version we have for this chapter of COE. Like we've manipulated in our lecture, right? Where it's better for chemical reactions, so we deal with moles. And there's a little bit of, bookkeeping, kind of being consistent and careful in all, because we got all these enthalpies that we talked about in the lecture. Okay, so we have moles instead of mass, right? Because we have our chemical balance, so it becomes easier to utilize this version when we have a chemical balance. All right, so we look at our boundary. There's no work happening in our combustion chamber here. So we get to get rid of that, right? And it's already showing kind of a steady state, right? So that's already assumed in this chapter, but I'll write it down. Okay. All right, so heat, and then we got the moles. So do we have, let's say, do we have the moles of the reactants? Do we have the moles of the products?
Would we have gotten those from our chemical balance when we found all the coefficients?
Yeah, so this is our, yep, so we have our actual balance, right? So this is our reactants right here, right? What's going in right here is our reactants, right? And then we have what's leaving, our products, which is right here. Okay, so this is our products, and this is our reactants, right? And I have it with the actual balance, right? Okay, so now it's the summation. So now we just got to kind of put everything together. But one step before that, what we want to do is put our temperatures in, okay? So in this problem, it's got a couple temperatures that make it a little more difficult. Let's move it over first. We have the products okay? That has a enthalpy of formation, okay? And then the enthalpy leaving in the products, right, is at 1200, okay? And then, does anyone remember what this enthalpy is? Or this one?
That was something to do with the reference or the reference state.
Yeah, it's the reference, okay? And that one, because it has that little circle there, right? This tells us, both of these tell us reference. Okay, same with here. And the reference is 25 degrees Celsius. Okay, so that means 298 Kelvin. Okay, so all our products are going to look like that. Okay, the reactants, they made it a little more challenging. They're at two different temperatures. The fuel's at 25, the air's at 12 underneath that writing I have, right? So that means, come on, computer, load. forever here. All right, there we go. All right. So we got to separate our reactants because they're at different temperatures right now. So we got to separate it at the beginning right here. So we have fuel, right? Which is has a reference formation. The fuel's at 25 degrees Celsius, so that's 298 Kelvin. And then the reference state is 298 Kelvin. Okay. So that's our first reactant. Okay. Then we have O2. And that one's at 12 degrees Celsius. So that's 285 Kelvin. And then you have N2 in the reactants. And that reference value always stays the same. It's always that 298. Okay. So again, this is the reactants. So this is the products, right? And then I separated the reactants already because some of them are at different temperatures, right? So we have reactants, and this one was at 298, the fuel, but then the air was at 285. Right? We have coming in here the air, fuel, right? And the air is oxygen and nitrogen, right? Any questions on that so far? All right, so now we get to write this a whole bunch because we got to expand the products, and I like to have all of it. All right, products. Let's go to our actual reaction. We have one, two, three, four. Okay. So that means this summation right here expands into four things. So we have NCO2, so this is all CO2, right? Then we have NH2O, and we have our N2 in the products. Our excess oxygen that's in the products. It's a lot of bookkeeping, like I said, like lots of writing with keeping things consistent. And now this is where we have a reactant. So that was all the products, right? Now we have our reactants. Fuel. Our oxygen in the reactants. It was at 285. Oh, that's 298, sorry. And then our N2. again, these are all the products. And then these were the reactants. And it matters with N2 and O2 can, they're in the products and the reactants, but they're at different temperatures in the products and the reactants. So that sensible energy matters. All right, we're running out of time. So we can now simplify this in actuality. Okay, so we can simplify this. We see things that are the same, right? So in the fuel, it's 298 minus 298. So this minus this ends up giving us 0. Okay. The other thing from lecture is the enthalpy of formation for N2 and O2 is 0. Okay, so we just helped ourselves on how much things we got to look up. Okay. The rest now is just a bunch of table lookups. Okay, so we get our enthalpy of formation values are table let me get the actual one instead of just saying tables for you.
On the enthalpy of formation for oxygen and air, is that 0 because it's like returning to, or it's because it's coming from the reference state? We're pulling it in.
Because it is stable at the reference state. So they pick basically to get enthalpy of formation values. They have to pick something to be the reference, and what's stable at atmospheric the 25 degrees Celsius, 1 atmosphere, is the enthalpy of formations that are 0, and then they calculate all the other enthalpy formations off of those. So like carbon, everything that's carbon, hydrogen, nitrogen, and oxygen all have enthalpy of formation of 0 because they're all stable at 25 degrees Celsius, 1 atmosphere. We have to do something to get the fuel at that, or we have to do something to get water or CO2. We have to have a reaction for that to occur from those.
Okay.
Okay, we have to form them from those O2, N2, C or hydrogen. Okay. So enthalpy of formation, or you can just look in that table and it'll show you 0 for those. Okay. So enthalpy of formation values are all from table A26. These other enthalpies are now temperature dependent. Okay, so those ones we have to get from the range of, that's all those tables we haven't used before. We haven't used that are in those molar values. So this is where now we have table A18 through A25. So for the per mole values, depending on which products you have, these are all the per mole enthalpy values. Okay. So all we do is it's just a lot of table lookups of getting these values and bookkeeping, like I said. And then the moles are all just from the balance. Okay. So in the products, we have 3 kilomoles of CO2. We have 4 kilomoles of H2. We have 7.5 N2 and 47 O2. Reactants, the fuel is 1. Oxygen is 2.5 and 2.5 times our A theoretical times 1 here, right? N2 in the reactants is our 2.5 A theoretical times 3.76. Okay, that is the moles for N2 in the products, or in the reactants. sorry. So it's a lot of bookkeeping, like I said, just carrying what you have down. And if we put all that in, put all those values in and calculate, we get negative 190,000, 4.64 kilojoules per kilomole of fuel. Okay, it's negative because it's out, right? They wanted rate. I'm kind of going fast. I'm way beyond time here, right? And that just means we need, this is per kilomole, so we need the molar flow rates. So moles flow rate of fuel for the times that heat transfer. And we have the mass of fuel. So all that is just dividing by the molar mass of fuel, and that'll get your molar flow rate of fuel. So if we do our units, 1.2 kilograms of fuel per minute, we had 44 kilograms of fuel per kilomole of fuel. And then we have our 190,464 kilojoules per kilomole of fuel. Check this units, the kilograms fuel cancel, kilomoles of fuel actually cancel here. So we just have kilojoules per minute. So we get 5,194 kilojoules per minute. Okay, so now that could be our heat in our gas turbine, right? If we think of now back in chapter 9, the heat that we were just saying heat in the combustion chamber, this could be it, right? Now we know the specifics of the fuel and air we're putting into the combustion chamber. This could be our heat in that goes in from all the way from our gas turbine chapter. So it connects those chapters. All right, I'm well beyond on time. I apologize for that, but it's good to just complete the problem in sequence. Any questions?
No class Wednesday, right?
Yeah, no class on Wednesday, and then Monday, your homework is due, and we'll do a review. And then the following, not this Wednesday, but the following Wednesday is your exam on these chapters. Okay.
Wait, no class on Wednesday?
No, it's Veterans Day. It's this
Oh.
Wednesday. Yep. So it falls right on our class day. Yep. I mean, you can join the Zoom. I'm not going to stop anybody from joining the Zoom, but I will not be there because I'm not allowed to be there.
Okay.
Also. But, all right. You guys have a good one, and I'll see you on Monday. Okay.
You as well.